Hi, I would like to welcome you all for the Keynote plenary session. This is number 5, and it's about how airborne transmission of SARS-CoV-2 confirmed the need for new ways of proper ventilation. This session is by Professor Dr. Philomena Bloschen, which received her first degree in 1986 from the Technical University of Eindhoven. In 1990, she received her PhD from Technical University of Denmark. Her thesis is about the air quality evaluated by a trained panel. After working for more than 20 years as a researcher with the TNO, where she coordinated, among other, several European projects on optimization of indoor environment quality and energy use. Then she was appointed a full professor indoor environment in 2012 at the Faculty of Architecture and Built Environment, University of Technology in Delft. At the TU Delft, she initiated the Sense Lab, a semi-lab environment partially open to public and sponsored by 25 companies and organizations, in which she recently performed research on the airborne transmission of exhaled aerosols. In 2019, Bloschen was appointed visiting professor at Ffp2 University in Taiwan. And she's a member of many organizations like Rehaba, ASHRI, TVVL, and other. She also a co-founder of the Dutch ISIQ chapters and was the first president of ISIQ in Dutch. She has contributed and authored to more than 250 publications and has been invited as a guest, distinguished, or keynote lectures at several conferences and universities. For her book, The Indoor Environment Handbook, How to Make Building Healthy and Comfortable, she received the Prestige Choice Outstanding Academic Title of 2010 award. Her book, The Healthy Indoor Environment, How to Assess Occupants' Well-being in Building, was published in 2014 and received the IDEC 2016 Book Award. So we'll begin with her presentation. Her presentation will be recorded. Also, this session is recorded as well.
Hello, my name is Philomena Bloschen, and I am Professor of Indoor Environment at the Faculty of Architecture and the Built Environment of the Delft University of Technology in the Netherlands. Before I start this keynote on how airborne transmission of SARS-CoV-2 confirmed the need for new ways of proper ventilation, I want to acknowledge a group of 36 colleagues from all over the world, especially Professor Lidia Marlowska. In March 2020, just after COVID-19 caused by SARS-CoV-2 was declared a pandemic by the World Health Organization, this group worked together to convince the world that airborne transmission is important to consider. Without this group, WHO would not have been convinced that airborne transmission is a serious route of transmission and therefore is important to account for in the fight against COVID-19. For the studies that I will present hereafter, I would like to specially thank Christoph Hermans and Gerrit Veenstra of the German-Dutch Wind Tunnel Institute, Professor Fulvius Coano of the Faculty of Aerospace Engineering, and Marco Ortiz and Dadi San of my own group. At the 5th of January 2020, WHO published the first disease outbreak news of COVID-19 on the new virus. 3 months later, at April 4, 1 million cases were reported. At the end of the summer 2021, worldwide, 228 million cases and 4.7 million deaths were reported. So, what do we know about this virus? We know that respiratory infections are caused by pathogens exhaled through the nose or mouth of an infected person. The pathogen, the coronavirus in this case, is aerosolized from sites in the respiratory tract during breathing, speaking, singing, shouting, sneezing, and coughing, forming so-called respiratory droplets. The coronavirus is therefore not naked, but encapsulated in water-based particles containing water, salt, protein, and other components that are part of our respiratory secretions and saliva. While these particles or respiratory droplets have a wide size range, most of them lie within the range from sub-micrometers to a few microns. The coronavirus itself has a size of around 120 nanometer or 0.12 micron in diameter. When exhaled, droplets can spread into the environment, depending on their size and weight. The blue particles shown in this figure are larger droplets that typically have a diameter larger than 100 microns, which fall to the floor under gravity within 2 meters of the source. The red particles are small droplets, also named aerosols, typically smaller than 100 microns, which can stay suspended for a longer time. How long and how far a droplet can stay or travel in the air depends on the droplet size and on the local airflow conditions, like air velocity, temperature, and humidity. In still air, particles of different sizes have different settling times. Based on Stokes' law, calculations show that in still indoor air, exhaled particles of a diameter between 5 and 10 micron take 8 to 30 minutes to fall to the floor from a height of 1.5 meters under the influence of gravity, while particles with a diameter of around 50 micron will take about 20 seconds to settle from a height of 1.5 meters. So, in still air, droplets smaller than 10 micron can remain suspended in air for many minutes. But the air indoors is not still. The distance a droplet theoretically can travel is shown here for low indoor air velocities, 5 centimeters per second. As you can see, a particle of the size of 5 micron can in theory travel up to 100 meters with low air velocities, while a particle of 10 micron reaches circa 25 meters. With high indoor air velocities, 20 centimeters per second, these distances can be a factor 4 further. Another aspect that can affect the travel of a droplet is the relative humidity of the indoor environment in which the droplet is traveling. As soon as a droplet is expired, the water part will start evaporating. How much will evaporate depends on the relative humidity and the temperature of the indoor environment, as well as the chemical composition of the droplet. In this figure, an example is shown of a droplet with a size of 10 micron containing visible levels of salt and protein before evaporation, and the chemical, its size after evaporation for different relative humidities. For a relative humidity between 20 and 80%, the droplet will shrink to around 4 micron, approximately 40% of its original size. For comparison, this CFD simulation shows you what happens with a droplet when a person exhales in air with a relative humidity of 35%, which can be considered dry air, and in air with a high relative humidity, 95%. In the dry air, the exhaled droplets will evaporate rapidly and continue as aerosols, whereas in the humid air, they will fall to the ground as droplets. Now, what are the best conditions for SARS-CoV-2 to survive? Recent studies show that with low temperatures and extreme relative humidities, so both with low and high relative humidities, SARS-CoV-2 stays alive the longest. With 10 degrees Celsius and the relative humidity of 40%, the half-life of the virus showed to be more than 24 hours, while at 27 degrees Celsius and a relative humidity of 65%, this was only about 1.5 hours. From that outcome, we can conclude that the usual recommended indoor climate conditions, a relative humidity between 40 and 60% and a temperature of around 23 degrees, is not so bad to strive for. Then we come to the question, how is SARS-CoV-2 transmitted? In theory, SARS-CoV-2 can be transmitted through direct or close contact with an infected person, through indirect contact via deposited or transmitted infectious droplets via surfaces such as a ball here. These are also named fomites, or through so-called airborne transmission, in which virus-carrying droplets produced by coughing, sneezing, talking, and even breathing are transmitted by the air, including both large droplets and aerosols that can linger in the air. So, when in close vicinity of an infectious person, this whole range has the potential to be transmitted, while when further away, the virus can be transmitted only by aerosols suspended in the air. This means that in theory, aerosols can be transmitted both by inhalation at short range and at long range. Although we do not know yet how much each of the different transmission pathways contribute, we do know that transmission through fomites does not or hardly takes place, and that close to the face of an infected person, the concentration of respiratory droplets of all sizes is the largest. So we can assume that there the infection risk is the highest, either by inhalation of aerosols or by deposition of respiratory droplets on the mucous membranes and further inoculation through the mouth, nose, or eyes. We also know from several outbreaks that long or far-range airborne transmission can play an important role in cross-infections of SARS-CoV-2. For example, during a choir practice in Skagit Valley in the USA, in a poor ventilated restaurant during Chinese New Year's Eve, on the much discussed Diamond Princess cruise ship, in a call center in South Korea, on a bus in Eastern China, and so on. Now the question is, how can we reduce transmission? To reduce direct transmission from mainly large infectious droplets, physical distancing has been adopted. And for indirect transmission, although we know now that this transmission route doesn't play an important role for this virus, cleaning surfaces and washing hands. For people who need to or tend to come close to possible infected persons, personal protective equipment is used, such as facial masks and protective gloves. From the information presented before, it is clear that physical distancing is a good measure to reduce the risk of transmission by large and small droplets. But it is also clear that it is false to assume that all axial droplets fall within this distance of 1.2 to 2 meters, and that therefore physical distancing in itself is enough in public spaces to prevent airborne transmission. It clearly is not. Therefore, the use of proper ventilation measures has been recommended to decrease the risk of far-range airborne transmission. This means, first of all, to provide sufficient and effective ventilation. Ventilation that ensures the supply of clean air and exhaust polluted, infected air from the breathing zones of each individual person, preferable without passing through the breathing zones of other persons, and without recirculation of air. If general ventilation seems not enough, or recirculation, reuse of air cannot be avoided, add air cleaning devices. Ventilation can be established by just opening a window, natural ventilation, or can be established by using a mechanical ventilation system varying from only exhaust to very advanced air conditioning systems that supply and exhaust the air. Mechanical ventilation gives the possibility to control the amount of air that is supplied, exhausted, and or reused, while natural ventilation is an uncontrolled form and therefore a less reliable way. Natural ventilation depends on several environmental aspects, such as the wind and temperature outdoors, but also on the dimensions of the space and the possibilities of having openings in the facade. Next to the type of ventilation, also different ventilation principles can be selected, such as mixing ventilation, displacement ventilation, cross ventilation, and personal ventilation. With mixing ventilation, the air pollutants are diluted and therefore reduces the number of infectious aerosols in the air. Displacement and cross ventilation move the air horizontally or vertically through space, ideally replacing polluted air with fresh air. To show the effect of different ventilation regimes on the distribution of aerosols exhaled by an infected person in a classroom, in the summer of 2020, we performed a series of tests in the experience room of the sensor at the TU. Infectious aerosols were simulated by air-filled soap bubbles introduced with a breathing system through a mannequin head. The first ventilation regime in the experience room was mixing ventilation with 1200 cubic meter per hour, or a ventilation rate of 17.5. And then half of that, 600 cubic meter per hour, or a ventilation rate of 8.7. Followed by having no ventilation. Then opening of windows. The opening of the door, internal ventilation. And then opening of both windows and door, creating cross ventilation. Finally, a test was performed, starting with no ventilation. After the build-up of the soap bubbles, the production was stopped, simulating the infected person was leaving the room, after which windows and door were opened. The tests with the different ventilation regimes clearly showed that aerosols can travel further than the 1 to 2 meter social distance recommended all over the world. The test also showed that exhaled aerosols build up in a poorly ventilated room, and ventilation with outdoor air helps to dilute the aerosols. Moreover, cross-ventilation, opening door and windows, after the occupants have left the room, clears the room the fastest, and seems a good strategy to use in, for example, classrooms. In the study of infected cases at secondary schools in relation to, among others, ventilation, which we performed in cooperation with University of Utrecht, the Medical Center of Utrecht, and the Erasmus Medical Center, We saw that this advice was taken very seriously in the past year. Windows and doors were open almost all the time, even in the presence of mechanical ventilation. As a consequence, many secondary school children were sitting with their coats on in the classroom, fighting the cold air from outdoors. Then face masks. The use of face masks by the public since the outbreak of COVID-19, obligatory or not, has led to diverse and numerous designs. But which masks should we choose? The surgical look-alike mask, probably the most used mask and by far the cheapest to buy, originally developed to protect the patient from the exhaled breath of a surgeon, a KN95 or FFP2 mask, developed to protect the carrier from pollutants such as fine dust, rather expensive and difficult to buy as a consumer. Or a washable mask made out of cotton or another fabric, with or without disposable filters that you slide in. Or even a mask you make yourself of old bed sheets. In the summer of 2020, we have visualized the leakage of the exhaled air for the first 3 masks. In the following movie, you can see this visualization, starting with the first mask, the surgical look-alike mask. A mist of water droplets colored with a fluorescent paint is produced and made visible by shining light on the droplets. The second mask we tested was the FFP2 mask. You can see less leakage around the mask as compared to the first mask. The colored mist tends to escape more upwards and less on the sides, but is still visible. With this mask, you have to worry less about the escaping aerosols when standing behind someone wearing this mask as compared to the previous one. And finally, the third mask, the cotton mask with a removable filter inside. Almost no leakage occurs. In any case, no visible leakage with the camera we used at that time. After this video went viral, at the request of many, we have studied the leakage that occurs with exhaling more in detail. Tests were performed with 14 different masks. With the use of the same breathing machine as in the soap bubble tests and the use of ultrasonic vibrations, water mist colored with a fluorescent tracking fluid was generated and exhaled by a mannequin head, as you can see here. These pictures show images taken from the side of the 4 masks I presented earlier, added with an image of the exhaled mist of colored droplets without a mask. The images clearly show that the mask prevents the exhaled aerosols from going forward, depending on the filtration capacity of the material and the number of layers used. For some masks, the droplets go right through the mask. It can also be seen that outward leakage can occur on the sides, going backwards, with the nose going upwards, or chin going down. The aerosols that leak are not exhaled to the front, but are sort of redistributed into the space. So also for those aerosols, ventilation is required. Then we arrive at air cleaning. Since the start of the pandemic, different filter or cleaning systems in a mobile form or permanent in the central unit, are used as additional measure indoors. Filtering of particles, for example, with HEPA filters, or cleaning with UVC light, the ultraviolet part of the UV spectrum that can inactivate bacteria and viruses. Most UVC systems make use of UVC with a wavelength of 254 nanometer, which is harmful to skin and eyes and can therefore not be used in the vicinity of people. UVC with a wavelength of 222 nanometer, on the other hand, is not harmful to people and has shown to be effective in inactivating, for example, SARS and MERS. What is, as far as I know, not available in the system on the market. Additionally, it should be noted that UV lights can only deactivate the pathogens that they see, and that in dusty ducts or rooms and air, passing pathogens may be shielded from the UV rays. To investigate whether a mobile HEPA filter system can be used as an additional measure in, for example, a classroom, we tested the cleaning effect with the air-filled soap bubbles, as well as the effect on sound and air velocity, draft risk, of a mobile HEPA filtering system for different settings and positions in the experience room of the sensor. It will probably be no surprise that this mobile HEPA filter system seemed a good additional measure next to natural ventilation. But it must be said that the system can result in unacceptable noise levels and draft effects, and the filter's cleaning performance depends clearly on the setting of the system and the position in the room. Also, more than one system will be needed in one classroom, causing an increase in noise and draft effects. Then we arrive at the key question: how much ventilation is required? This is not an easy question to answer. Current guidelines for air quality indoors are based on the CO2 concentration in air that is allowed. CO2 is used as an indicator for the presence of people. With every breath we take, we exhale CO2. With the equation shown here, it is possible to calculate the required ventilation rate per person in a space to keep below the allowed CO2 concentration. The air distribution effectiveness in that equation tells us something about how effective the air is distributed. For complete mixing, this value is 1. When we use natural ventilation, opening windows, single-sided or two-sided, this effectiveness can vary depending upon the temperature differences, wind direction, and dimensions of the space. Now, assuming a limit value of 1200 ppm, an outdoor concentration of 400 ppm, and a seated adult producing 18 liters CO2 per hour, this would result in a required ventilation rate of 6.25 liters per second per person for a ventilated room with an effectiveness of 1, and twice as much for a room with an effectiveness of half. Whether these values are enough to prevent transmission is not known yet. Of course, we can ask ourselves whether CO2 is a good indicator for exhaled infectious aerosols. CO2 is a gas, and exhaled aerosols and droplets are no gases, and most likely don't all behave as gases. Or could it as a proxy be true for aerosols? If CO2 is a good proxy for exhaled infectious aerosols in, for example, classrooms, where do I place the CO2 sensor? And is one sensor enough? Recent studies in the field, as well as in the Sense Lab, showed that CO2 concentrations can differ significantly in a classroom, depending on the ventilation regime. A classroom with natural ventilation would require at least 2 measurement points, one on the wall opposite to the facade with the window, and the other on the wall nearby the teacher. Additionally, it was found that the outdoor CO2 concentration can also vary per location, but also during the day, which implies at least 1 CO2 sensor outdoors as well. In the case CO2 is not a good proxy for exhaled aerosols, which is very likely, are there other models we can apply to estimate how much ventilation we need? To cope with the risk of airborne transmission, the most used model has been the Wells-Riley model, presented here. Based on this equation, it is theoretically possible to calculate the infection risk for a certain ventilation rate and the number of persons present, assuming one infected person. Unfortunately, this model or equation has a number of limitations, such as that it does not account for the differences between persons. Not every person responds the same upon exposure to the virus, and not every infected person releases the same amount of quantum infectious material. Furthermore, it is assumed that the concentration of infectious aerosols is homogeneous in indoor spaces, or in terms of ventilation and mixing situation. And it is assumed that over time, this uniform concentration is constant, and therefore the ongoing inhalation of the concentration is constant as well. Nevertheless, the Wells-Riley equation is useful in gaining insights into generalized infection risk for a range of certain situations. And in terms of ventilation, these may possibly best relate to measures to reduce that airborne risk at a larger population scale. However, to those seeking workable solutions at building level that reduce cross-infections through improved building design and ventilation measures, the use is limited. In any case, it is clear that ventilation of a space will decrease the concentration of possible infectious aerosols. How those infectious aerosols will distribute and possibly meet a healthy person on the way that can inhale them is difficult to predict with ventilation at room level. To really reduce the risk on transmission to nearly zero, you will have to exhaust the possible infectious aerosol as close as possible to the source. Personal ventilation seems then a possibility, under the condition that the directions of the airflow are considered as well. Most available personal ventilation systems are focused on supply of fresh air into the breathing zone, not on the exhaust, but of course, many other possibilities are thinkable. What is important not to forget is that infectious aerosols are not the only possible pollutants present in a space. It has taken several decades to convince the authorities to account for other sources of pollution than people in the space. Think of emissions of construction and furnishing materials, the outdoor air, pollutants originating from bad maintenance of ventilation systems, and not to forget all those volatile organic compounds and particles that are released during the many activities we, as occupants, perform at home, the office, school, and so on. Moreover, it is important to account for the other indoor environmental factors that interact with measures we take with respect to ventilation. Opening a window can introduce noise from outdoors, but also can introduce the cold air during winter time. Last winter, many children at our schools were suffering from this, sitting in classrooms with windows and doors open in order to get enough fresh air, but also in situations with a mechanical ventilation system. Problems with noise from the increased airflow in the ducts, the so-called rustle of the air, have increased because systems were put on their max possible airflow for as much ventilation as possible. Not to speak about the drafts this can cause. In conclusion, assuming airborne transmission of SARS-CoV-2 is a route of transmission that seriously needs to be considered, it is clear that the question is not only which ventilation rates are required to protect against infection transmission, but also how should one ventilate for a certain situation. It is important now to rethink ventilation, specifically for indoor spaces with a high density of people during a long period of shared time, such as educational settings, offices, hotels, restaurants, hospitals, care homes, theaters, and gyms. The new generation of ventilation systems should not just focus on the ventilation of a space, but provide a range of ventilation options that fulfill the demands of the occupants over time, whether related to health or comfort. Flexibility is therefore the key. What COVID-19 has shown us is that we desperately need to get a better understanding of how pathogens spread within buildings, what the best conditions and ways are to combat them, but also how we can create affordable, efficiently, and effectively ventilation designs. Research is still clearly needed, but cooperation with different disciplines, such as epidemiologists, virologists, aerosol experts, building engineers, architects, and behavioral psychologists and ventilation experts is indispensable. Moreover, the combat of future diseases should be taken up hand in hand with the climate change challenges we are facing. Thank you for listening.
Okay, this is the presentation, and I would like to thank Prof. Dr. Filomena. However, she couldn't attend this session because some personal reasons. So if you have any question, I encourage you to send her to her email. And thank you for the attendance, and see you in the next session.